There we go. Okay. So just to recap, we've got solutions. Okay, and substances that are dissolved in water are aqueous solutions. How many of us have not heard what the word aqueous means? No one, not all of us know what aqueous means. Okay, have we heard of aqueduct? Maybe on like a documentary about Rome. Okay, what's still saying no? Okay, what about aquifer? Okay, what's on board now? Okay, what's an aquifer? Something to do with water, probably. Okay, Ben, what are we thinking? Yeah, aquifers are places where water is stored, typically underground. Okay, an aqueduct helps us to transport water. Okay, what do those two things have in common? Water. Okay, and then in the name of the word, what do they have in common? Aqua. Okay, so if we say it's an aqueous solution, can you kind of see aqua in the word aqueous? Just a little bit. Okay, it's kind of hidden in there. Okay, aqueous means water solution. So if I make chocolate milk out of like whole milk and chocolate syrup from Hershey's, is that an aqueous solution?
No.
No, why not?
Because it's milk, not water.
It's milk, not water. Okay, what about if I say, okay, I'm going to get some orange juice concentrate and frozen from the can because I don't want to have to squeeze all that orange. Okay, if I take that and make it according to the instructions, okay, is that going to be an aqueous solution?
Yes.
Okay, why? Because yeah, you add concentrate, that frozen stuff, to water. Okay, so aqueous solutions are always going to have water as the stuff doing the dissolving. It's going to be the liquid typically. Okay, now we've worked with a couple of other liquids where we've made solutions. Have we worked with methanol before?
Yes.
Yeah, what did we dissolve in methanol? Citric acid. Ivan's got really good memory. Okay, if we take citric acid and we put it into methanol, what happens to it? It dissolves. Okay, if we have something dissolved, does that automatically make it an aqueous solution? No, we have to pay attention to what we're dissolving it in. So citric acid in methanol is not aqueous. Okay, it is a solution. Okay, just like Mountain Dew is a solution and coffee is a solution and a lot of other things are solutions. Okay, but what's important is if it's aqueous or not. Okay, so then let's talk about this thing called a solution. Again, this is stuff that you guys already know. I'm just giving you the words to describe it. Okay, so if we say that solutions are homogeneous, okay, if we say that solutions are homogeneous, can I get 2 glasses of Kool-Aid from the same pitcher and they're going to taste exactly the same? Can I do that? Yeah, I mean, if it's mixed well, okay, you can get 2 glasses of Kool-Aid or punch or whatever that tastes exactly the same, even though they're 2 different glasses. Okay, now we've got 2 new words on here. We've got solvent and solute. Okay, solvent, okay, we're going to talk about this in a little while, but solvent is typically going to be water. Okay, and solute is going to be the thing that is dissolved. Okay, it's going to be our sugar, our salt, our, chocolate syrup. Okay, it's going to be the stuff that goes into a liquid to be dissolved. Okay, biggest thing with these though is that if you pass a solution through a filter, does anything get left behind? No. Okay, because they're both in sort of this liquid, aqueous, kind of dissolved state. If I take methanol and citric acid, mix them up, what are they? If I say citric acid and methanol, what happens to them? Just, they're dissolved, okay? If I pass that stuff through a filter, can I get the citric acid back out? Through a filter. Citric acid and methanol, mix it together. Okay, we've got like a very small, no. Okay, that's okay. Okay, we are not going to be able to get the solvent and solute to separate using a filter. Okay, and they don't settle with time. Think of like a snow globe. If we've got a snow globe and we shake it up, okay, what happens to all the little snow particles? It goes everywhere. Okay, what happens when we set it down on the table? It falls down. Thanks. So if we see that this stuff starts to settle, so think of like orange juice with pulp. What happens to the pulp after a little while? Goes down to the bottom. It's like the worst glass of orange juice you've ever had if you forget to shake it. Okay, until the very end, you're like, oh man, I've got like an inch left. Let me shake it. It's like all pulp. Okay. we're going to make sure when we're looking at solutions that this stuff isn't something that's going to settle or fall out over time. Okay, and then something that's really weird. Okay, we've got solvent and solute. Okay, two parts of a solution. Okay, they can be solids, liquids, or gases. Okay, now liquids, you guys kind of get, if we add concentrate to water, okay, concentrate's kind of a liquid. Okay, and liquid water is, well, it's a liquid, right? We can mix two liquids together, and that's fine. Can we mix a solid and a liquid together? Yeah, what kind of solid could we add to water? Sugar. Okay, give me another, Sky. The packages of stuff. Oh, like a instant lemonade or like a Gatorade packet or something, right? We're adding powders to liquid, okay? These things, right? That's a solid into a liquid. Okay, now what about gases? What gases could we dissolve into a liquid? Or could we?
Can't even stuff gases.
Maybe when you mix up battery, you get bubbles trapped in it. Okay, here's another one that I know you guys are familiar with. Okay, how many of us have had Mountain Dew? Okay, keep your hands up. All right, thank you. All right, how many of us have had Sprite?
Yeah, but it's not.
Okay, how about root beer? How about sparkling water for those bougie people? Okay, all right. So sparkling water, soda, anything with bubbles in it, what do we call that? What do we call those bubbles? Carbonation. Okay, carbonation is dissolved gas, gas in water. Okay, how do you guys think fish breathe? Very carefully, they stick a straw up to the surface and they just like scuba dive the whole time. Okay, now their gills, right? How many of us have taken biology yet? Most of us have taken biology. Okay, so what do the gills in fish do? Ben, what do we got? They take oxygen from the water. Now, does that mean that they're taking one? They're like, you know what? I'm going to steal oxygen from this water molecule. And so now it's not H2O, it's just H2. Is that what they're doing? No, Whit's just like, no, not at all. No, no, stop. Blasphemy. Okay. What the gills do is they pull out that oxygen that's dissolved in water. Okay. That's how fish can, breathe. Okay. That's how they survive. They get oxygen that's dissolved in the water. They pull it out and then they're happy-go-lucky. Okay. So let's look at some other parts of solutions. Okay. If we've got substances that can dissolve most readily in water, things like sugar, salt, okay, these things are going to be ionic or they're going to be polar and covalent. Okay, we're going to talk about what those two words mean, or really three words: ionic, polar, and covalent. Okay, we're going to talk about what those mean next trimester. Okay, but suffice it to say that ionic and polar compounds are similar in characteristics to water. Okay, water is something that's polar. Okay, if we think of our lab that we did last unit where we had the chalk, sugar, and citric acid, what was the name of that lab? Do you guys remember? The name of the lab that we did to separate our mixture. Folding paper one with the filter. Okay, the name of that lab was likes dissolves likes. Okay, if something is similar to something else, it is able to dissolve it. Okay, so water being polar, okay, can dissolve things that are ionic and things that are polar. Can it dissolve things that are non-polar? No. Okay, right, I mean, yeah, it's right there, okay? But if I didn't even give you that sentence of non-polar covalent compounds do not dissolve in water, could you pretty much guess that things that are non-polar won't dissolve in water? Right, because water is polar, and if they're two different compounds, like black and white, completely different colors, okay, or not colors, two completely different compounds, okay, they're not going to dissolve very easily. Okay, so how many of us have tried to make like a vinaigrette at home or like a fancy salad dressing? Okay, a couple of us have, okay, or like those crazy like lava lamps where you put water and oil together and you put like a Alka-Seltzer tablet in it, okay, and you see the bubbles of oil float and rise, okay. Those two components don't mix together, and that's following our golden rule. Okay, miscible is when two different liquids can dissolve in each other. And immiscible is when they can't. Okay, something that I use to kind of remind myself what that means is miscible means mixable. Okay, and immiscible means, well, not mixable. Okay, it only goes so far, that little way to remember. But mixable, right? If we look at our flask right here, we've got yellow liquid and blue liquid. When we mix them together, if they're miscible, what color do we get? Green, okay? What happens if they're not miscible, if they're immiscible? We'll have yellow and blue, we'll make a nice little stack, okay? And just like Whit pointed out, we'll have a nice layering effect where maybe like this section would be blue and this one would be yellow. Okay, we're going to layer these things because they're not mixable, they don't combine. Okay. Now, really quick, I told you guys I would talk about solvents and solutes. Okay, so solvent is something that does the dissolving. Typically, it's going to be water. It's going to be our most common solvent. Okay, in fact, I memorized water as the universal solvent. Okay, solute. Okay, this is something that I struggled with learning this. Okay, solute is going to be something that gets dissolved. Okay, solute is going to be our sugar and our salt. Okay, and to remind you of what solute is, okay, think of us like we're in a branch of the military. Okay, you could say Army, Marine, Navy, you know, whatever you want to say. Okay, whatever branch of the military you want to be in. Okay, and you say, all right, let's say we're all standing, you know, we're getting yelled at for not marching well enough and we're not cleaning enough things. And man, these, you know, we're just getting yelled at for everything. Okay, we're all standing at attention, right? When the commanding officer, all right, or our general or captain or whatever is done yelling at us, okay, what is he going to say to get us all to kind of leave and go about our business? Goodbye. Well, he's going to, what is the like the official thing that they say in the movies? Well, maybe not at ease, they would just be stand still. What do they do to get rid of them? Dismiss. Thanks, Matthew. So we've got, you know, a commanding officer telling you dismiss. Okay, or in our case, we could say dissolve. Okay, what do all of the guys and gals standing at attention do when he says dismissed? Yeah, Liberty's got it right. Okay, they do a little salute. Okay, and then they just spin around and leave, like Ivan was saying. Okay, so when we are dissolved, okay, we're breaking apart into our groups. Okay, we're gonna salute or solute, and then break up. Okay, it's kind of a weird way to think of it. Okay, but it kind of works, right? If you follow it along. Okay, I don't know, it helps me, right? I've struggled with this in high school, and I'm still struggling with it because I'm still using this weird little salute mnemonic device. Okay, so how do we feel about this? Again, this is stuff that you guys already know. I'm just giving you new words to associate with this. Okay, who feels like they need a break? I mean, it's 6th hour. We're almost done. Who needs a bit of a break? Okay, I mean, you know, this is a horrible question. I'm still going to ask you guys to do sciencey stuff. Okay, but if you notice, Davidson out, he's got his iPad. Okay, what happens when Davidson's got his iPad all ready to go? We get to play the game, and he's going to try and trash all of y'all. Okay, so let me pull up the game. Pull out your iPads. A lot of them should still have them. Okay, a lot of you guys should still have iPads on the desks. Okay, and what we're gonna do, another one? Really? All right, let's see if I can. I cannot remember the password, so I would get a new one because I don't remember the password. Okay, or Davidson's gonna come in and save the day. I don't remember it. Okay, so what I'm gonna do, we're talking about phase changes. Now, when did we talk about phase changes? The other day, last week sometime, right? How many of us, be honest, okay, be honest, how many of us don't remember the phase change information? That's totally cool. That's totally cool. Okay. Yeah, liquid solids, you know, what happens when we heat up a liquid, what happens to the particles. Okay, a lot of us don't quite remember this, and that's okay. Okay, because this assessment, definitely not for a grade. This is for bragging rights to say to everyone, hey, we beat Davidson. Okay, because I'm not going to be playing this one. Okay, I'm going to be moderating a little bit. Okay, so let me hit play. Do you guys want to do classic or teams? Okay, raise your hand for teams. Okay, 1, 2, 3, 4. Okay, raise your hand for classic. 1, 2, 3, 4, 5. All right, let's do classic then. Okay. We're going to go for 5 minutes. I'm going to give you guys $5,000 each.
Oh my God.
Okay, $5,000 each. This is going to be great. Okay, I won't say anything except for please trash Davidson. Don't let him win. All right, so let's get going. Okay, make sure we're actually using our names on this. Okay, if you feel like, oh my gosh, I put a Q in my name and my name's Ivan. Why would I put a Q in there? Okay, just let all right, just let me know and I can, you know, give you a chance to try again on that name. So far, everyone's doing Brandon Witt a Q. No, I'll let it slide. That's pretty great. Lime elephant. I got to get rid of the lime elephant. I don't know who that is.
Don't get rid of bleach.
All right, who was a lime elephant?
Who isn't a lime elephant?
Apparently me. All right, let me double check how many people we got today. 2, 5, 7, 8, 12, and then another 12 is 24, 26, I think. I think we should have 26 people if I'm counting right. Anyone not see their name on the board? Okay, Aubrey's missing it. Davidson, you on there? Davidson's like the 5th one on there. Bo's on there. All right, Ben, you want to join us? So now, all right, cool. You don't always have to play these things. They are fun. They're pretty chill. Okay, I will tell you these questions are going to be pretty similar to your test. Okay, all right, 25. All right, let's go. Wait, Liberty, what happened? That's weird. What? I haven't had this kind of technical difficulty before. What's happening here?
I don't know, it's not working.
Maybe try a new page. Join. Who just happened? Weird. Okay, so if your name is already on there, you should be joined. Okay, when I hit start game, you should be able to jump back in there. Okay, okay, Liberty's on there. All right, let's try this. Okay, let's see if it works. If it really didn't let you in, you can join partway through. So don't worry about it. All right, 3, 2, 1, trash Davidson. That is a lot of money. Okay, why does it not change temperature during boiling? Okay, this one, okay, we talked about it a little bit, but I don't think I really emphasized it. So let me take a moment and do that. Okay, if we've got our temperature curve for phase changes, okay, what happens when we're heating up ice? Okay, show me with your hands what it looks like. Okay, yeah, we're kind of increasing, okay? What happens when we get to 0 degrees Celsius and we have ice? Okay, I've got a couple people going like this and a couple people going like this. Okay, Blake's going up, thanks, man. Okay, I appreciate, hey, you had a 50-50 chance on it, okay? So when we're changing states, when we're doing a phase change, such as boiling, okay, the temperature does not change, okay? And the reason why is because all of the energy that we're putting into there isn't being used to change the temperature. It's being used to change states. Okay, up until the point that we get to 100 degrees Celsius, if we're heating up water, we're applying heat to it, what happens to its temperature as we give it some heat? It goes up, all right? And like you guys still using that, I appreciate it. Okay, as we put, pot of water on the stove, it's a liquid. So when we turn the stove on, we put some gas or an electric burner on it. Okay, it will start to increase the temperature until we get to 100 degrees Celsius, at which point it stays the same. It does not change to temperature. Again, the reason for that, think of like our revolving doors. Okay, who here remembers the revolving door analogy for these phase changes? Seen a couple nods and seen a lot of tuning out at 6 hour. Okay, that's okay. Okay, I'm gonna keep talking for the people that are confused about this and want to get some hints and help, because this will be on the test. Okay, so with our phase changes, if we're thinking of our revolving doors, okay, once we get to 100 degrees Celsius, okay, what happens with our water, we start to have more and more people go outside the building. Okay, so as we put more and more people through the revolving door, okay, until every single person that was once on the inside is on the outside, until we get everyone switched, everyone through the door. Okay, one, we don't have a full phase change, and two, we don't have a temperature change. Okay, and remember, temperature change, if it also helps, temperature is a measure of an average speed. Just because I have steam doesn't mean that we're changing temperature. It's an average. Our thermometer is in a liquid. The hottest a liquid can get at these conditions with the pressure that we've got is 100 degrees Celsius for water. Okay, so 100 degrees Celsius for water is the hottest our liquid can get. Okay, we'll talk about this some more on our review, because we'll have review on Wednesday. Okay, and we'll have review next Monday before the test. Okay, but it's okay that you guys struggled on this. This was something that we pretty lightly talked about, so it's okay. All right, now let's look at the rest of our notes. Okay, so we took a nice little break to make sure that we were going to be good. Okay, because when did we talk about those phase changes again? We talked about them last week, like Thursday or something. So that's been a little while. So we want to make sure that that's staying fresh in our mind and that we can remember those things, and in addition to this stuff, because they're both going to be tested on. Okay, so then let's look at, there's Gim Kit time. Okay, let's look at how dissolving works. Let's bring it back to dissolving. Okay, if we are going to dissolve something, does it happen without us stirring it or heating it up? It's spontaneous, okay? It doesn't require much effort on our part to dissolve something. So if I put a piece of rock salt in a beaker of water, is it going to start dissolving? If I just put it in a beaker of water, is rock salt going to dissolve? No? Whit's saying yes, Addie's saying no, okay? Whit, why are you saying yes? Because it's salt, okay? How do we know for sure? Maybe did we have an experience with it? Did we do this in the lab at some point? Yeah, we took rock salt and we put it in a beaker, and even if it took forever, okay, it still ended up dissolving without us having to heat it up or stir it or do anything to it. So dissolving is going to be spontaneous. Okay, does that mean it's going to happen fast? No. Okay, spontaneous says nothing about a speed. It just says that it's going to happen. Okay, that's all it says. Doesn't say anything more, doesn't say anything less. All it says is it's going to happen whether we like it or not. We can speed up the process or slow it down. How would we speed up the process of dissolving? Yeah, we could stir it, blow on it. How do we make our chocolate syrup dissolve in milk faster? You can stir it. Okay, what if we're trying to make hot chocolate? How do we dissolve our hot chocolate mix into our water? You heat it up a little bit. I mean, it's in the name. It's called hot chocolate for a reason. The hotter it gets, the more we can put into it. Okay, so the next three parts, okay, are really the three steps of dissolving something. Okay, so what I want you guys to do, I want you guys to clap your hands together, okay, and intertwine your fingers. Okay, or if you don't want to do it that way, you can do like, I'm in the sound of music. You could do it this way. Okay, either way works. Okay, while your fingers are intertwined, while your hands are locked together, I want you to try and pull them apart without unintertwining your fingers, okay, or without bending them, right? You can't. It's kind of tricky. Blake's doing it, but he's like, gotta, breaking the force of nature here. Okay, so it is tricky to pull our fingers apart when they're intertwined or locked together like this. Okay, so breaking the attraction between different solute particles, so breaking the attraction between different salt particles, we'll use salt as our example, breaking that attraction is really hard. Okay, we have to pull them apart, takes energy. Okay, our second part, solvent particles are moved apart. Okay, how many of us have been to a concert before? Okay, and I don't mean like a nice classical music concert. I mean like we're going to Fall Out Boy or Plain White Tees, something. Okay, we're going to a concert, and let's say we got to the standing room only part. We got like some hot tickets. Okay, we're going to the space right in front of the stage. Okay, but you showed up a little bit late, right? How easy is it for you to go from the back of the crowd right up to the stage? It's not happening. Okay, and if it is happening, you gotta be like Andre the Giant and like the Princess Bride and be like, everybody move, right? You gotta, start parting the Red Sea here. You gotta really just elbow your way in. Okay, that takes energy. Okay, so moving water particles apart, moving our solvent apart takes energy. Okay, so breaking things apart and kind of moving them to the side takes that energy. Okay, our last step, solute particles are attracted to solvent particles. Okay, what I want you guys to do, show me your hands again. Okay, if we've got our hands together, I want you to clap them together. Okay, I appreciate the applause. I'm here all night. Okay, if we've got our hands clapping together, okay, what are we doing? What are we giving out? We're giving out some form of energy. How are we giving out energy? Sound. Okay, when we clap our hands together, we start making a sound that's releasing energy. If you clap your hands a lot, what ends up happening to your hands? Well, they get a little bit raw. Do they kind of start to feel a little bit warmer? So like if it's in the winter and you're like, got to warm up my hands, right? If you clap your finger, yeah, you could do this, right? But if you were lazy and you didn't want to do like this and you just clapped your hands together, they'd start warming up a bit. Okay, so bringing things together, fusing them together, okay, releases energy. Okay, it feels weird because I know a lot of you guys are probably in biology. Okay, and biology says, oh, when you break down sugar, it releases energy and it takes energy to form sugar. Okay, that's true, but there's a lot more complicated stuff going on in there. Okay, what I want you guys to remember is when we're forming an attraction, we're releasing energy. If we're breaking an attraction, we're taking energy. Okay, so what I want you guys to think of, let's think about someone that's got really, really good chemistry together, two people, okay? Maybe like you and your crush, right? I don't care if it's a crush at the school or a celebrity crush. I was gonna say, I see you, Ivan. Okay, you're eyeing some people in the back, all right, okay. Hey, you don't have to admit who your crush is, okay? But if you're pretending that you and your crush are together, right? You've got perfect chemistry, okay? When you get together, right, what is the girl going to say to the guy if we're talking about a guy-girl relationship? They're going to say, oh, you're so hot. Oh my gosh. Okay. They're going to get this really high voice, be like, hi, how are you doing? They're going to go all cheerleader voicey, right? Sorry if you guys are cheerleader, you all have really high voices and I don't, and I have a highish voice, but anyways, okay. They're going to go all girly and flirty and fun. Okay. What's going to have to happen if we're trying to break up that couple? You're going to have the third wheel friend. You're going to have maybe like, someone's cheating. You're going to have like some sort of high energy drama. Okay. And it's going to take a lot of energy to break you away from your crush, right? How many of us had a crush on Justin Bieber? Thanks, guys. Okay. If you have a celebrity crush, it takes something massive for you to break your undying fealty to them, right? So that's how breaking attractions is. Breaking these interactions that molecules have with each other. Okay, forming them is easy. Forming them releases energy. Okay, breaking them apart is what's problematic. Okay, so then if we look at our next step on page 7, we're talking about endothermic and exothermic. Who in the world, or who has no idea what in the world those mean? Totally be honest, guys. I had no idea what these meant until I learned it in chemistry either. Okay, exothermic means that we are giving away energy. Energy is leaving our system, leaving our beaker. Okay, this energy could be in the form of anything. Okay, but if we're looking at exothermic, what do you think that energy is going to take form as? Did I hear it somewhere? I think I heard it. Oh, you didn't say anything? Okay. Also, in case I didn't tell you guys, my ear is acting up, so I can really only hear in one ear. So if I ask you to repeat something, it's okay. It's not your fault. I just can't hear. Okay. So if we're looking at exothermic, okay, how is energy going to be released? Heat. Okay. Think of like thermals, right? Let's see, this is Utah. We're going skiing all the time. Best way to prepare yourself for skiing is to wear a pair of thermals, right? So thermal energy, heat, is how we're looking at endo versus exothermic. Okay, in the space underneath your page on the bottom left, bottom right, something like that, on page 7, I want you guys to write down endo and exo. Okay, after you guys finish writing down this space. Okay, write down endo and exo. And next to the exo, you're going to write a negative sign. Next to the endo part, you're going to have a positive sign. Okay, so endo is going to have positive sign. Exo is going to have negative. Okay, so let's talk about what this means for a little bit. Okay, if we've got temperature increasing as we're dissolving something, that means that it's going to most likely be exothermic. Okay, its exothermic processes outweigh the endothermic ones. Okay, if temperature is decreasing, that means that our endothermic processes are going to outweigh our exothermic processes. Okay, so let's take a break from science. Let's talk in terms that we probably all understand a little bit. How many of us have a bank account? Whether it's checking, savings, whatever, we've got something. Maybe we at least have a piggy bank at home. Okay, if we're looking at our bank account, let's say I start with $600. Okay, I'm a college student, I'm poor. Okay, if we've got $600 in our banking account, okay, but I have to pay gas. Okay, when I pay my gas bill or my electricity bill, okay, what sign are we going to have showing in my, transaction summary? We're going to have a negative, right? Yeah. So when you have something leaving your bank account, you see a negative sign. Okay, when something comes into your bank account, like a paycheck, what sign do you see there? Plus sign. Okay, so think of your bank account like a beaker. Think of it like your beaker account. Okay, if we have heat or cash coming into the beaker, okay, what sign are we going to see for heat coming into a beaker? Positive. Okay, if we have heat leaving the beaker or cash leaving our beaker, what happens? What sign are we seeing? Negative. Okay, I like you guys doing like the negatives and the positives. That's great. So if we're looking at something being positive or negative based on the heat transfer, okay, let's talk about what this feels like now. Okay, you guys got this pretty well set and solid. Okay, let's talk about what an exothermic reaction feels like. Okay, exothermic reaction. How did we say the heat was transferring with an exothermic reaction? Is it going out of the beaker or coming in? Out. Okay, with exothermic reactions, heat's leaving our beaker. Okay, so if I touch the beaker, is it going to feel hot or cold? Heat's leaving the beaker. Okay, raise your hands if you say cold. Okay, all right, raise your hands if you feel hot. Okay, a couple people saying hot, a couple people saying cold. So this is where it starts to get a little backwards feeling. Okay, but I promise it's not. It makes sense. Okay, What I want you to do, think of endothermic being like a vampire. Okay, what do vampires do? They want to suck your blood, okay? If we've got something that's endothermic, instead of sucking blood, what are they gonna suck? Heat, okay? They're gonna suck heat out of their surroundings or your hand. Okay, so what I want you guys to do, touch either your chair leg or your table leg, okay, something that's metal. How does it feel? Cold, okay? So would you say that the metal is being a heat vampire?
No.
No? Who said no? Why would you say it's not? Would it be? No, Liberty's shaking her head no. Okay, if you're sucking heat away, say it one more time, Liberty. Exactly. So things that are vampires are going to suck heat away. They will feel cold. Okay, when we tell that something is hot or cold, right? If I want to see that the burner on my stove is still hot, what am I feeling? You're feeling the heat transfer into your hand, and hopefully not too much. You don't want to cook your hand, right? But you're feeling heat transfer into your hand. You're not feeling the heat itself. Okay, it's a weird concept, but you're feeling a heat transfer. Okay, if I feel like a ice cube, how is the heat transferring? Is it going into my hand or out of my hand? Out, okay? So if we have an ice cube sitting in my hand and it's going out, what temperature is it gonna feel? Pretty cold, okay? So when I say it feels hot, it feels cold, I'm asking which direction is it transferring energy? What I'm going to do now, I'm going to give you guys about 5 minutes or so. I want you guys to look at these application questions on page 7. Okay, page 7 has if potassium chlorate were dissolved in water, would the temperature increase or decrease? So work with your partners for the next couple minutes. Finish these. The information that you need to answer these is on the table on the right side of your page. Okay, it gives you information about does it take heat or does it release heat when it is dissolved. So take a couple minutes, okay, and then we'll do a quick little wrap up of all of this. All right, so I'm seeing you guys start to pack up a little bit. We do have a couple minutes left. We can still work on this, okay? But again, make sure you can answer those questions. They'll be pretty similar to our test. Okay, now, before we put our packets away, okay, I know this is horrible timing, okay, pull them out really quick. Let's just go through one more slide. Okay, just one more. Okay, what I want you guys to do, let's go to, make sure I can actually bring it over here. Okay, let's go to our next page, page 8. Okay, solubility of solids. Okay, now this is a lot of information, which is why this is the only slide we're doing for the last part of class. Okay, in general, okay, when we add a lot of our solute, someone remind me of what a good example of a solute would be. Sugar, salt, okay, any other examples? Kool-Aid is also acceptable. I would take Kool-Aid, okay? When we add a lot of our salt, sugar, Kool-Aid, baking soda, whatever you want, okay, if we add that to our solvent, okay, our water, then we will start dissolving it until we reach what's called the saturation point. Okay, is there a point where we can't add any more sugar to water? Yeah, what happens to the sugar when we try doing it? It turns into kind of a sludge at the bottom, right? It's the nastiest part of the drink because it's all grainy and gross. Okay, we can add lots and lots of sugar to our water, but eventually we'll reach a point where we can't do anymore. And we'll make that sludge. It won't dissolve. Okay. Once we get to that point where we've added as much as we can, it's called a saturated solution. Okay. And because I've got like 30 more seconds, I'm going to hit the next slide because I can. Okay. When we get to, double check, yeah. When we get to saturation, okay, we do not have any more change in our system. Okay, it's not going to dissolve anymore. It's not going to make things fall out of the solution. It's not going to form crystals. It's going to be a perfect solution. Okay, we're going to have some particles of solute move to the solid state. We're going to have some of them go from the solid to the aqueous state, and it'll go back and forth. Okay, but when I say there's no net change, there's no net change. It will be a constant equal flow. Have a great day, guys. Make good decisions. We'll see you tomorrow.